Okay, so now let's take a look at application of orthogonal projections. So let's say we have a sailboat that has a constant velocity, which is given by the vector v, 3, 4. So we're going 3 units to the right and 4 units up. So let's just say in red, here is our vector v. And then the wind has a constant velocity, and the wind's vector is given by this vector w, which has 10 minus 10. So it is going off, the wind is blowing in this direction. And then we might want to ask, well, let's find the component of the force that is in the same direction as the sailboat's motion. And we can find the component of the force which is perpendicular to the sailboat's motion. And so we would like to find the component of the force W, which is this vector in blue, that is in the direction of the sailboat's motion. And that's this vector right here, V. And so we can see here is that this vector in yellow is actually going in the exact opposite direction as the boat's velocity V is taking it. So that tells me that this wind vector is actually going against the motion of this sailboat moving in this direction. So the wind is hindering the motion of this sailboat. So we can find the projection of W onto V, this yellow vector right here. It's going to be some scalar multiple of V. It has to sit on the same line as the vector V. And we found that the formula for finding that scalar is we take the dot product of W with V and then divide that by the dot product of V with itself. So in this case, taking the dot product of W and V gives us 30 minus 40. So we get a minus 10 for the numerator. And then for the denominator, we would take the dot product of V with itself. So that's going to give me 3 squared plus 4 squared, which gives us 25. So the projection, the orthogonal projection of W onto the direction V is equal to minus 10 over 25 times V, which we can simplify plugging in the vector V. This would give me minus 6/5 and minus 8/5 would be the resulting projection, orthogonal projection of W onto V. So we see that this scalar is negative, and that again is because the projection is in the exact opposite direction as the motion V was. And next, although we're not asked to do this, we can find the component of W, which is orthogonal to V, that I'll denote with Z by saying, well, once we figured out what the projection onto the direction V is, then I can just say W minus this projection gives me the missing piece Z. So down below, we can find this orthogonal projection by taking W, which was the vector 10 minus 10, and subtracting the projection that we just found, which was the vector minus 6/5 minus 8/5. So taking 10 and subtracting a negative 6/5 gives me 56/5, and taking minus 10 and subtracting a minus 8/5 gives me a minus 42/5. So when we project the vector W onto the direction V, we get this yellow vector, which was minus 6/5 minus 8/5 that we denote with W hat, or the projection, the orthogonal projection of W onto V. And then this second vector that we got is the remaining piece of the vector in green that we often denote with a Z. And in this case, that is 56/5 minus 42/5. And then we can double check our work to make sure that if I take W hat and Z, so if I take the orthogonal projection and the component which is orthogonal to V, if I add these back together, I should get back the vector that we started with. And you can verify that indeed adding the projection to the orthogonal piece gives us back the original wind vector, which was 10 minus 10.